My name is Adrian Bejan. I've been teaching at Duke since 1984. I have all my degrees from MIT. Before that, I was trained to be good at more than one thing, and those other things were mathematics Olympiads, art, meaning making drawings, and playing basketball at the highest level. My activity is in thermal sciences, which means three things, essentially. One is thermodynamics, or the science of power, the power that drives everything that moves, meaning everything that's useful to us, but also all of life on Earth. Number two, heat transfer, which is the science of heating and cooling, and also devices that facilitate those flows. And the third is the concept of evolutionary design, or design in nature, which includes everything. In fact, the thermodynamics and the heat transfer and the design that I just mentioned constitute one subject, which is the science of design, or the science of form and then evolution of form in the direction of greater usefulness. My research is the same as my teaching. One is the other, like the hand in the glove. And the courses that I teach are on thermodynamics, which are illustrated in the book covers that I'm putting in this video. The same with heat transfer. And when it comes to evolutionary design, also known as constructal design, I have spearheaded that domain of science as well. My view of scholarship, which, by the way, is what I'm teaching to the students who come to me, is that the primary purpose of being in university is to learn how to engage productively in doing creative work. Creative work, as the word indicates, means the ability to come up with new ideas, and then with the force to implement those ideas, with the audacity to do something different, something that may be more useful. And that means that in my courses and in my research and my publications, I'm teaching the freedom to question, the freedom the courage to express original ideas or points of view, and also the freedom to question others about their claims of goodness in the realm of creative work. All these things, in my opinion, make the good university, the good department, and the good spirit that inhabits the enclosure we call school. First, words have meaning, especially in science. Evolution means the changes that are occurring in a discernible direction in time, discernible to the observer. In fact, all of science comes from what the observer observes and discerns. Second, freedom is the one word for all the physical features that endow the object or the system with the ability to change. No freedom, no change, no evolution, no configuration for that matter, because configuration comes from an evolving design, and that means no direction of time and no future. Now, it may surprise you to know that freedom can be measured. We can measure it, as I will show, as the number of degrees of freedom that the object has at its disposal. And also, freedom can be measured in terms of the effect of these degrees of freedom on performance, efficiency, and benefit to the user. We get this idea even better if we question the meaning of evolutionary design. Here I have an icon of where we all come from and where we're going. everything in nature is a moving system that morphs with freedom. This is an icon of the book of Thermodynamics. We call it thermodynamic system in the blue domain is powered by heating from a source. This energy stream is converted partially into work or power, and the remainder is discharged necessarily to the ambient. In the blue domain, I sketched many configurations, some very old, some a lot newer, and they suggest that the design that facilitates the converting of heating into work has been evolving. So that is evolutionary design, and it's only half of the picture. The complete picture is shown here in the rectangular box. The previous drawings are in the blue domain called engines, with what I just told you around the engines, heat in, heat out, and work out. The point is that the work is dissipated instantly by moving something against its will, that is, against its environment. That movement dissipates the work completely. It dissipates it into heat. So from a distance, and if you look again at the rectangular box, heating in, and then heat rejection 100% from the rectangular box. But in the meantime, or inside the box, movement has happened in the horizontal direction on the Earth's surface because of the presence of evolutionary designs, both in the blue domain and in the green domain. So the designs are evolving toward being better, which means that through evolution, the movement itself becomes farther and more efficient and longer lasting. To account for this new aspect of the thermodynamics that we practice, I stated in 1996 the Constructal law. I'll read it to you. For a flow system to persist in time, this is the definition of to live. It must evolve with freedom such that it provides a greater access. Let me explain. This is the physics definition of life, because in thermodynamics we already have the physics definition of death. It's called the dead state, or the being of a system where nothing moves. There's no flow, nothing changes. The boundaries are not showing deformations over time, and so on. So the life state is the antonym, if you want, or the opposite of the dead state. Important here is are the three words shown in bold letters: to live with, and then to change with freedom, where the greater access. These words really mean one and the same thing, which is freedom itself. Because without the physical features that allow changes, then there is no life, and meaning there is no movement, and also no access. I have here an example of a laboratory demonstration of the evolution in time of a river basin. From time frame to time frame, the architecture is changing, it is morphing, it is always tree-like or arborescent, but there is a direction in time which you can show through measurements. It is toward flowing more and more easily, meaning the water on this horizontal area being driven by gravity by smaller and smaller peaks of let's call it altitude. The green is really sand, originally of uniform thickness, on the floor of a laboratory. And so the movie plot from left to right is in fact the time arrow, which is brought into thermodynamics by this statement. One more thing, evolution, the concept, is as old as science itself. It comes from the Latin verb evolvo evolvere, which means to roll out, to roll forth. This word makes the mind think of the image of childbirth. Everything that is born or nascent is due or it comes out of Mother Nature, a feminine entity. Natura in Latin means that. This is a mother word that has given birth to many other words in the language of science that we speak today. I mean the word valve, vulva, or Volvo, the brand name in the Swedish automobile. All these words have the same origin as evolution itself. Now, with this law of physics, many researchers today have shown that it is possible to predict not only the evolutionary designs that have been observed and documented, but also to predict the future of these designs over time. This is a panel of the designs that endow all sorts of systems on Earth with locomotion, that is, movement driven by power, swimmers, runners, and flyers. You have here a surprising agreement between the observed speeds of locomotion versus body sizes. The body sizes cover a huge territory from the housefly to the biggest ships. This unification of movers on Earth is a drawing coming from me that has been evolving over time. The ships are the most recent addition. They show basically agreement with the swimmers. The airplanes, they appear to be deviating from the line of the flyers. More recently, they've been brought in line with the flyers, with the animal flyers, by taking into account the fact that the density of the medium in which the fastest airplanes are traveling is sensibly lower than the density of the atmosphere against which animal flight is designed. And so this success, which is the agreement between all these dots and the theoretical lines shown here as two parallel lines for flyers and swimmers, this success is accompanied by a cloud-like distribution of data, a diversity, if you will. Very soon you will see a blow-up of this region of the fastest movers versus the body sizes. And that is how the next idea comes on the screen. The cloud itself is about diversity hand in hand with the predictable trend. And this is a blow-up of that right-hand extremity of the previous drawing. We have the body sizes, we have the speeds, and here you see in each of these groups, flyers, runners, and swimmers, that the fastest are not the biggest. The biggest animals are somewhat slower than their fastest relatives. And this hump has been used by many as an argument that the general trend is incorrect. And the slogan of that particular point of view is that the biggest are not the fastest. It turns out that, in fact, the biggest are the fastest. What we have here as coming from zoology are the maximum speeds. And of course, the maximum speeds of animals have to do with the lifestyle of the animals. So the fastest animals, flyer, runner, or swimmer, are in fact the predators. The really big animals that are fast are not the fastest, are the grazers, the ones that move all the time and of course eat all the time. So the speed average over the lifetime of the mover turns out to be in accord with the prediction that the trend is toward greater speeds, average speeds, as the body size increases. You can see this very clearly if you think about the evolution of airplanes. We have big commercial jetliners that are fast, but not the fastest, yet they fly all the time. They spend their lives almost entirely flying, compared with the lives of fighter jets. Well, the jet fighters are spending most of their time hidden in the hangars underground. So, in other words, just like the cheetah is mostly at rest. The lion is mostly asleep. The house cat is mostly asleep. Yes, all of them are fast, just like the sprinter in the 100-meter dash. When the feeding time comes. There is a diversity everywhere. No one would confuse the hummingbird with the albatross, or the house cat with the lion. And this diversity has its own physics, meaning physics, if you know it, then with that you can predict the diversity. You get that idea if you make drawings the way I do. I make them all the same size, you see. And so comparing the cat with the lion, we notice here that the cat is mostly belly, small legs. The lion is showing more legs as opposed to belly. And the elephant is even more exaggerated in the direction of greater legs. It turns out that with physics and, of course, the mechanics of the lifting organ, which is in this case the legs or the wings here, or the undulating tail in the case of the swimmer, the mechanics of this periodically flexing lifting organism calls for this relationship between the body fraction occupied by the lifting organ in the entire size of the mover. In this direction, that of course I hope is of interest to you, the audience. I continue with the examples of the artifact with a reference to the problem or the need to cool a finite volume, which is shown as a rectangle here, a finite volume that generates a fixed rate of heating, and this volume is populated with objects that are generating the heat. The drawing has 1 degree of freedom, which is the spacing between these staggered plates. And there are 3 designs. The extreme on the left has big spacings, which means few plates. The one on the right has many plates and tiny spacings. And of interest here is how hot the whole box gets. Clearly, it's hot on the left and hot on the right. It's in between, meaning the coolest that it can be in the middle. And this is the discovery that comes from having endowed the drawing with freedom to morph. And so the recommended spacing or the recommended number of plates is the secret worth knowing. This secret has been carried in many directions during the past 2 decades, from left to right. That direction points toward more than 1 degree of freedom. From the left is the same heat generating package cooling problem, this time cooled by forced convection. And then, as you can see, the staggered design has more than 1 degree of freedom, because you can vary not only the spacings, but also the spacings between the columns of these plates. We have tubes, a bank of tubes in cross flow. There are vertical spacings, horizontal spacings. There is also a choice to be made between the pattern, a triangular or square, and so forth. And on the right, we have the heat sink populated by a little forest of pin fins. That is another configuration, 3-dimensional, to which I will be returning shortly. Another way to remember the secret of evolutionary design, in this case with 1 degree of freedom, is that the so-called recommended or optimal spacing, the choice spacing between those plates or small plates, is such that the spacing is of the same scale as the thickness of the boundary layers that coat each plate. So the boundary layers are invisible, but they're actually visible in the imagination of you, the viewer, who has studied heat transfer from my textbook. So if you know the boundary layer thickness, you know how to size the spacing between these heat-generating components. So now the recommended spacing is here in the middle, or in this package of vertical plates. Therefore, the design is such that in the box you install the boundary layers the way that you would install crayons in a crayon box. But another way to remember it is that in each channel, the flow itself is developing, and it is developing along a length that matches the entrance length of the flow. So the other name for this entire design philosophy is entrance length design. This idea has been extended in several directions, including in the 3 dimensions. Here's an example of entrance length design for a package of 2 streams in cross flow. There's a purple stream entering as a sheet from the left and flowing upward through 5 fingers, each finger of entrance length dimension. And then a second stream coming in blue from the right, and then proceeding to the left with its own 5 fingers of entrance length. That's what you do with a concept. Here's another concept that comes from having liberated your thinking in the direction of evolutionary design with freedom. This is the problem that kickstarted the Constructal law and then its applications. There's the problem of cooling a rectangular space, shown here with a white perimeter, rectangular space that generates heat uniformly, and the space is occupied by a material of low thermal conductivity. Inserted in that box is a blade of very high thermal conductivity, very much like the rivulet that carries the water out of the area occupied by the 2 hill slopes. And that's the configuration, and the freedom that it has is in the shape of the rectangle. Here I have 3 examples of shape. One is shallow, the other one is robust looking, and the objective of the entire artifact is to cool the entire space the most, which means to avoid the color red, which is evident here and evident here. It is less pronounced in this middle drawing, and the middle drawing teaches one thing, which is that the shape speaks of the balance between resistance horizontally to heat flow and resistance to heat flow vertically. And that balance is also expressed graphically as a finger of high thermal conductivity inserted in its own glove of low thermal conductivity. So that's the beginning. If you give this idea even more freedom to morph, as shown here, in other words, not only one finger, say the big one, but three, the other two smaller, then each finger comes with its own glove, the small one with thinner gloves, and this way you end up with a arborescent architecture of inserts, each trunk and branch bringing with it its own sleeve, its own glove. And in this direction, more such add-ons, meaning more degrees of freedom. Among the degrees of freedom are all these angles between tributaries or branches, and so on. So on this slide, what emerges is the philosophy of vascular design, which is in fact the big, now grown-up baby of the original problem for heat conduction. Similar architectures have been developed for convection. This is in fact from the cover design of the fourth edition of my textbook, Convection Heat Transfer. Here are pictures of the temperature distribution affected by a coolant, actually cold fluid, exiting from the center and invading a plate that generates heat uniformly. In these other two panels, the coolant comes from the right, and the heating in two dimensions comes from the left. Another way to look back at what most of us know about cooling packages that generate heat is to summarize the behavior of the heat transfer density in the package versus the length scale, capital L, of the package. If the package is cooled by natural convection, meaning updraft, as in my first example in this presentation of spacings, then the heat transfer density on this log-log plot is increasing monotonically as the length scale of the package decreases. If the package is cooled by forced convection, that behavior continues, but at a faster rate. If the same package is cooled by solid body conduction, as in my more recent examples, then the progress toward the greater heat transfer density at smaller scales is even steeper. So, with this story of the evolution of cooling technology, we have a crystal ball in which we see the phenomenon of evolution everywhere in nature. It is gradual, and then boom, it is replaced when the species is outcompeted by a new species. And the new species rules the landscape when it is outcompeted by yet another species. It doesn't mean that the previous species are vanishing right away. It means that in the direction from low density or to greater compactness, the landscape populated by these designs becomes more complex and much more effective in removing heat transfer from packages of, in this case, electronics. Now, why is it natural for the direction of evolution to be from the lower right to the upper left, toward smaller scales? The answer to that question comes from this drawing. Here's the component. It could be the avionics on an airplane, or for that matter, the heart on a bird. And that component could have any size.
So the size is the lone degree of freedom that we're discussing. We know from thermodynamics that a flow component destroys useful energy or exergy because of friction in flow passages or heat transfer across finite temperature differences, which are finite because the heat transfer surface that's pierced by the heat current is not of infinite size. So when the size of the component increases, the irreversibilities associated with the component decrease. And this is an attractive direction in which to think. It turns out that this is a mirage, because in the same direction of greater size, the size of the suitcase that the big mover has to carry, the suitcase is called a component, increases, and along with that increase comes the increase linear, really, in the destroyed exergy because of having to carry the component. So the trade-off between the two dashed curves proclaims the existence of a recommended organ size for a particular body size. This is why big trucks have big pumps and big birds have big hearts. And now the answer to the question that I just posed before the slide has to do with the fact that with evolutionary design, the flow architecture of the organ improves. Again, from flow through parallel tubes to flow through arborescent or tree-like tubes. And that means that this descending curve has in its nature the tendency to migrate downward. That means that the drawing morphs. Here is the descending curve migrating downward. And that means that the sum of the two curves, the one shaped as a bucket, has its bottom dropping and the lowest point migrating to the left. Where? Toward smaller sizes. So the emergence of smaller components on finite size movers on the landscape is natural, because in that direction the movement of the big is facilitated more. So freedom at the level of the component evolution translates into rewards for the movement of the big. The big is, of course, the beneficiary of all the designs that inhabit it. This is the reality shown here graphically with the image of naked man, then naked man with a nature-inspired tool, and these days naked man with the tool and with the next or future tool generated by the human mind. This is the let's say the add-on due to artificial intelligence. The important observation to make here is that in evolution, what works is kept. The wrench did not make the naked hand obsolete. Let's call it the intelligent arm will never make the plumber's wrench obsolete. You see? So in evolution, what works is kept. The diversity that I just illustrated is not random. It is organized into hierarchies. We get this next idea by looking at, frankly, anything that means population on the globe today. Here's the population of models of airplanes versus on the abscissa their year when each model was adopted. On the ordinate is the size of the flying body. Obviously, this is a hill or a mountain, the crest of which is rising over time. The biggest the models, are joined, say, a decade later by even bigger models. But that's the trivial observation. The subtle is that at any particular time during one given decade, the new models are arriving in all sizes, small and large. And even more subtle is that the new models that arrive are such that the small are many, they're all new. Small are many, and the big are few. And that is called hierarchy. It's more evident if we look at all the flyers beginning with the birds and of course pterodactyl. The point is that in a two-dimensional plot of population size versus body size, qualitatively, there's a straight line on a logarithmic plot, a descending line from the many small to the few large. In other words, design in nature, the organization of flow systems happens, it just happens in this way, hierarchically, not in one size. And why? Why is this? Once again, because of physics. And the answer comes as a kind of a two-punch move in a boxing match. The first punch is economies of scale. You can show with pencil and paper as a homework problem that a stream of water that flows, one stream of water that flows through two parallel pipes of equal size flows a lot more easily through a single pipe that's more voluminous, a single pipe that has the same volume as the original two pipes. In other words, the change in flow configuration toward flowing more easily is from 2 to 1. That's economies of scale. You can write the equivalent problem by thinking of two small bodies, two barges on a river being pulled against drag. The barges are loaded with coal versus a single barge that's bigger, carrying the total load of the first two. You can show that the power required to drag the big one is considerably smaller than the power required to drag the previous two. So the change toward easier flowing from physics is from 2 to 1. And if this is the tendency in nature to flow more easily, then why is it, or why was it, that not everything that's moving on the landscape is big? The reason is that the flow on the landscape is not from one point to another point, as in, the simplest problems of geometry. It is between one point and an area. The direction of the flow doesn't matter. It is because it's about the fact that the point is one and the area means an infinity of points, or between a point and another infinity of points called volume. And for the flow to cover the infinity of points, well, that flow must have access to smaller and smaller and smaller pockets of territory between the bigger territories that have been served, were wetted, were swept by the big movers anticipated or recommended by economies of scale. So we arrive in this way at hierarchy. Another word for hierarchy, or the natural emergence of hierarchy, is called organization, or coalescence of living things or movers. You see that in this photograph that I took two photographs. Seagulls on the roof of a cottage on the seashore facing the breeze. They they do two things. Actually, the three things. First, they come together. Second, they face the wind the same way. Third, they space themselves such that the ones in the wake have the same spacing as the vortices of the Karman vortex street, meaning that each of the trailing birds is feeling a relative push from behind, from the wind that swept downstream, and that push from behind makes the trailing bird a lazier worker in its legs, meaning it has to do less work to stand up straight in the wind. Here, the upper photograph is about cranes, the way that they are oriented when not working, oriented in a strong breeze. The front of the crane is this one, the one loaded with a weight, meaning the beak of the crane bird is on the left, just as it was in the lower photograph. This hierarchy or organization is on display everywhere. The movement of people on an area such as the Atlanta airport, few large and many small. The one large is the train. The many small are the pedestrians on the concourses. This drawing, Atlanta airport is an icon of the natural emergence of the city block, with walking perpendicularly to the smallest alley. Freight on a larger area moves the same way. The same freight is being vehicled on the area by few large trucks and many smaller trucks proceeding transversally. The so-called food chain is really the coexistence of few large movers with very many movers that cover the area in the other direction. And the biggest example of this type of hierarchy emerging naturally on Earth is the movement of humanity on the globe. This is the air travel 20 years ago, illustrated by NASA in terms of the measured condensation trails behind all flying aircraft. You see where the flying is going on. That is where the red is the heart with the two chambers of air travel. The whole globe is traveling, and so the movement is hierarchical, and that means that the fuel consumption is hierarchical as well. This hierarchy was not dictated by the General Secretary of the Communist Party. This happened naturally, and with that idea, we can now admire another version of the facts. Plotted here are facts about economics, hand in hand with the technology of driving movement on the planet. Fuel is being burned, of course. From fire comes power, from power comes movement, and you see here that annual fuel use is essentially proportional to annual wealth, known as gross domestic product. And so the conclusion then is that there is a rough one-to-one proportionality between annual fuel use and annual wealth. We've already established that fuel use emerges hierarchically naturally. That means that the hierarchical distribution of wealth on the globe is hierarchical, is natural as well. So the natural phenomenon that gave birth to hierarchy in air travel is the same physics that makes wealth hierarchy unstoppable, if you will, on the globe. The subtle point about this graph is the time arrow of all the dots that occupy this yellow band. All the dots are racing upward. Listen to government reports every year. Doesn't matter which country you're concerned with. Governments are interested in greater wealth or increased GDP for their population. And that means, of course, necessarily an increase from year to year in fuel consumption. And that brings me to the concluding idea, which is that the science as a construct of the human mind, an empowering construct, is itself a evolutionary design, evolving in this direction of time that I just illustrated. I have a way to illustrate that with the evolution of thermodynamics itself over the past 200 years, from its origins, originally caloric theory and mechanics, and then 150 years ago, thermodynamics, almost 60 years ago, the corralling of the long-lost child of caloric theory called heat transfer back into thermodynamics, and then today, meaning starting with 20 years ago, bringing in the evolutionary designs, the designs that in fact are responsible for the thickness of every single thermodynamics book. Every thermodynamics book is about contrivances that have been getting better over time, techniques for producing power from fire or producing heating and cooling from the same fire. Those drawings are in the books. Well, they've been evolving. They've been evolving over time. And now, with these three roots into the very fertile ground of human ingenuity, we have a thermodynamics that's, I think, much better position to advance forward. Now, there's a subtle story that goes with the movie that this drawing is like the poster for a movie. And it is that the march from left to right is punctuated by individuals. From left to right, the evolution of science is speaking of the importance of freedom in the march toward performance of any evolutionary design. My concluding slide is of the opposite kind, which is this doesn't require any explanation, except that the punchline is that march in columns, do not climb peaks. So that's essentially the lecture for today. On the left, I have the keywords that I spoke, and I invite you to contemplate and use or improve. On the right, if you'd like to learn more, please study the new book, Freedom and Evolution, Hierarchy in Nature, Society, and Science.